welcome to CEC lectures. Myself Dr. Preeti Trigwani. I am an associate professor from Department of Computer Science, Aribhat College, University of Delhi. So in this lecture series of advanced data structures and algorithms, now we are going to start with one of the new modules which is known as maximum flow problem. So today in this lecture we are going to introduce that maximum flow problem, and then we will be looking into a relevant theorem which is max flow min-cut theorem. Now when we say maximum flow problem, it is about finding a maximum flow through a directed graph, and we will be taking one source which is one place in the graph, one node in the graph, and from that particular node in the graph we will be looking for a flow, how much flow it can be taken to another portion or to other part of the graph. So more specifically when I am talking about the flow, so that comes from a source vertex, let us say S, and ends into a sink vertex, let us say T. Now each edge in the graph, as it is a directed graph, the graph is having direction, and also it is a weighted, we are talking about a weighted graph. So each edge in the graph is defined, is given a weight, not only a single number, but the two numbers there. One number indicates the flow, another number indicates a capacity, where capacity, if I talk about, is the maximum flow that the edge can have. So for example, you can see the figure which is available on the screen. So S here is, I can take it as a source, and after this we have the vertices V1, V2, V3 and V4, and finally we have a sink node which is known as T. So you can see that this node S, which is considered as the source node, is not having any incoming edges. So that means the flow is going in the out direction from S, while if you look into this sink node T, this is not having any outgoing edge, but all the edges here are kind of incoming edges. And please notice in this figure that every this we can say edge is given two of the numbers. So for example, there is an edge from S to V1 and the numbers written as 0/3. Then from V1 to V3 again that is 0/3, from V2 to V1 that is 0/5, and from S to V2 that is 0/7. So two numbers indicated on each and every we can say directed edge. So one number, as I have already told you, is going to be the flow, another one is going to be the capacity. So flow is, we can say, how much traffic, how much data is currently flowing on that particular edge, and what is going to be the capacity is what maximum flow that edge can handle. So for example, in the present figure, if we look into the edge which is starting from S going to V1, this is having 0,3. So 0 is the present flow and 3 is the capacity. So presently it is an unutilized we can say path or unutilized edge, as all other are there, and the total flow which we can give to this edge is 3. And as far as from V2 to V1, the maximum flow which can be pushed into is 5. Then from S to V2, the maximum flow which can be pushed into or which can be pressed into is 7. So these two numbers indicate, one is the current flow which is kind of the capacity which is utilized, and next after the slash, the number which is indicated is the maximum flow, nothing but the capacity. So this is how a flow network, we are going to read this flow network. Now why do we need to find a maximum flow from one particular source node to a sink node which is T? Now this problem of finding maximum flow in a graph can have varied number of applications. So this could be for planning the roads in a city to avoid some future traffic jams, whatever the current kind of flow is, how much capacity is, and then we need to see that how much expansion is required and so on and so forth. So one is an urban planning. Now another similar application could be to assess the effect of removing a water pipe or maybe an electric wire or maybe a network cable, then how other connected pipes or wires or cables are going to be affected in terms of flow. That can also be kind of determined with the help of maximum flow theorem, or even we can say to find where in the flow network expanding the capacity is going to give us the maximum possible flow. So the purpose here is to increase kind of the data traffic, or it could be a physical traffic, or it could be a water flow. So if we want to increase the flow, where should we hit upon so that we can achieve maximum flow, or we can say in order to find the bottlenecks, this network flow is also going to be useful. Now before going into the relevant theorem of max flow min cut theorem, we will be looking into some terminology first. So as till this point we have seen, a flow network is what we call a directed graph with a flow flowing through it. Then if we talk about the capacity, which is mostly denoted by the term C of an edge, tells us how much flow is allowed to be pushed or to be pressed into that edge or through that edge. And the third one is each edge also has a flow value that tells how much the current flow is in the edge. So the flow value is written before the slash and the capacity is written is written after the slash. So that is what the convention, writing convention is. Moving on next with the terminology, here we can see there is an edge from V1 to V2, 0/7 is there. So the edge shown here as a flow and a capacity which are described as 0/7. This means that the flow is 0, capacity is 7. So the flow in this edge can be increased up to 7 maximum, but not more, because beyond 7 the capacity is not available with this edge, or the maximum capacity of this edge is 7. So we cannot push a flow beyond a total of 7, we can say. Now if we talk about this problem of this flow network, we can say in its simplest form, a flow network has one source S where the flow comes out. As I have already shown you in the example that there are no incoming edges on the S. So that means whatever flow is present is going to be come out, there is no incoming edge, and there is going to be a sink vertex T where the flow goes in, and this sink vertex T is not having any outgoing edges, and the other vertices will have just the flow passing through them. And this is also a rule that whatever flow is coming on to all other internal nodes, that much of amount of flow must go pass on. So for example, there is a vertex, let us say V1. So from different edges, V1 is getting a total of let us say X amount of flow. So that X amount of flow has to be kind of passed through that V1. V1 is not supposed to keep any amount of flow with it. So that means the total of the incoming edges of a particular vertex is going to be the total of the outgoing edges as well. So for all vertices, what I can say here is except S and T. So this rule is not going to be applied to S and T, because S is not having any incoming edges and T is not having any outgoing edges. So for all the vertices except S and T, there is a conservation of flow, and this statement or this example which I have just given you is known as conservation of flow, which means that the same amount of flow that goes into a vertex must also come out of it. So, two conditions we have seen till now. One is the total flow cannot be greater than the capacity, and for all other vertices except S and T, there is a conservation of flow. Whatever flow goes into the vertex, that must also come out of it. Now, what are the methods of we can say calculating this maximum flow? So, we have kind of standard algorithms which are available for calculation of this maximum flow. So, one of the very famous algorithms obviously which we are going to study in our upcoming lectures is Ford-Fulkerson algorithm, or we can have Edmond-Karp algorithm. And these algorithms basically work by sending more and more flow through the edges in this flow network until the capacity of the edges reaches to its maximum, or we can say until the capacity of the edges are such that no more flow can be pushed into. So, iteratively they keep on increasing the flow until the whole path or until the whole edge's capacity, complete capacity of a particular edge is being utilized. Such a path where more flow can be sent through is called an augmented path. So, augmentation actually kind of we can say in terms of addition. So, such a path where more flow can be sent through is called an augmented path. Now, when we talk about these two algorithms which are very famous algorithms for calculation of these maximum flow things, one is Ford-Fulkerson as I have told you, and another one is Edmond-Karp algorithm. These both are implemented using something which is called a residual network. Now, let us try to see what actually this residual network is. Now, residual, as in when we talk about the term residual, is whatever is left over, whatever is kept aside kind of thing. Leftover is the proper term for this. So, the residual network is set up with residual capacities on each edge. Now, what is the residual capacity? This residual capacity of an edge is the capacity on that edge minus the flow. That means whatever capacity is left. So, for example, between V1 and V2 or between any two vertices, the capacity is let us say 7 and the current flow is let us say 3. So, the edge is written as 3/7. So, what is the residual capacity here? So, residual capacity is going to be 4. So, residual capacity of an edge is the capacity on that edge minus flow. So, flow is 3, capacity is 7. So, 7 minus 3 is 4. So, when the flow is increased in an edge, the residual capacity is decreased with the same amount. So, for example, I am increasing a flow by 2. So, now the flow is 5, the capacity is 7. So, it is 5/7. So, what is the residual capacity? The earlier residual capacity of 4 was 4. Now, the residual capacity is 7 minus 5, which is nothing but 2. So, 2 by an unit of 2, if the flow is increased, then obviously the residual capacity, which is the leftover capacity, is decreased with the same amount. So, after finding these residual capacities, residual networks, the next step is for each edge in this residual network, there is also kind of a reversed edge that points in the opposite direction of the original edge. So, which says if the original edge is from V1 to V2, there is a reverse edge from V2 to V1. Now please understand, the residual capacity of the reversed edge is the flow of the original edge. So for example, flow of the original edge is 5, that is going to be the residual capacity of the reversed edge. Now why do we need these reversed edge? These reversed edges are actually very important for sending the flow back on an edge as the part of the maximum flow algorithm. So it is not only the residual networks or the residual capacities which are going to be utilized in our flow network or maximum flow algorithms. We also need, reversed edges and the residual capacity of the reverse edges as well, and these reverse edges are important because these will be utilized for sending the flow back on an edge, and sending this flow back on an edge is actually an important what we can say is component of this maximum flow algorithm. Now before going into these two maximum flow algorithms, which are Ford-Fulkerson and Edmond-Karp algorithm, we need to understand one small theorem with the help of some examples. So the theorem here is known as max flow min cut theorem. So in order to find that max flow, we are going to we can say divide the graph into two sets of vertices with the help of a cut. So one set of the vertices which is on one side of the cut is going to be in one partition, or we can say in one set. The other side of the cut, all the vertices on the other side of the cut will be in the next set of vertices. So basically what are we going to do? We create two sets of vertices, one with only the source vertex inside in it, and the source vertex here is nothing but S, and the next one with all other vertices inside it, including the sink vertex. So S is going to be the one set of the vertices, and all other sets V1, V2, V3, V4 plus T, which is the sink vertex, is going to be on other side of this partition, we can say, or will be in the other set of vertices. Now what are we going to do by drawing this kind of cut? So now starting in the source vertex, we can choose to expand the set S by including the adjacent vertices and continue to include adjacent vertices as much as we want, as long as we do not include the sink vertex. So basically in the initial stage we are having S and all other vertices in two different sets. So we keep on expanding the set S as long as we do not include the sink vertex. So S when included with V1 may have kind of S and V1 in one set of the vertices, then again expanded S, V1 and V2 on the one side of the sets of vertices, V3, V4 and T on the other. So in this way, edges by edges, we are going to kind of expand, we chose to expand this set S, and as we keep on expanding the set S, that will automatically keep on shrinking the set T, because ultimately we have a finite number of vertices. We are increasing the vertices in one set, or we can say we are changing the set of vertices from T to S. So expanding set S will definitely shrink the set T, because any vertex belongs to either the set S or to set E, but not to both of them. In such a setup, when we talk about the term cut, so with any vertex belonging to either the set S or set T, there is a cut between the set, or we can say, in a layman language we understand it by there is a boundary wall between the set S and the set T. So, one side it is having the set S and its vertices which are included after obviously the expansion, and another side it is having the set T which is having the vertices which are left after the expansion of set S. So, there is a cut between the two set, and the cut consists of all the edges stretching from set S to set T. What does it mean? That we will see. So, here we have a graph which was the earlier graph, in which you can see there are 4 vertices other than S and T. So, one and the dotted lines here are showing different cuts. So, here are we can see 3 cuts. One cut is A, another one is named as B, and third one is named as kind of C. So, let us say for example, there was initially it was only the set S which was on one side, and all others V1, V2, V3, V4 and T on the next. Now, let us say we start expanding this set S, and we included V1 into that, and now we have our cut as the cut A. So, on the left side of cut A you can see S and V1 vertices and all other vertices V2, V3, V4 and T on the other side. We start expanding, or we keep on expanding, and then we included V2 also in the set S. So, S, V1 and V2 on one side of the vertex, V3, V4 and T on the another side, and we have as you can see, this is our cut B. And then if we keep on expanding more, so maybe in 2 other steps we can have our V3 and V4 also on the side of the S, and also only the last sync vertex, which is the vertex T, on the right side of the cut, which is nothing but the cut C. So, if you can see A, it is having a cut in which S and V1 on the one direction, V2, V3, V4, T on the other. If you can see B, it is having S, V1 and V2 on one direction, V3, V4 and T on the other. And if we see the cut C, so V4 and even S, V1, V2, V3, V4 on one side and T on the other side. So, this is what your the concept of cuts is. So, after establishing this cut, what are we trying to do? If we add all the capacities from the edges going from the set S to set T, we are going to get the capacity of the cut. And what is this capacity of cut? This capacity of cut is actually the total possible flow from source to sink using that particular cut. And the theorem says max flow min cut. So, minimum cut is the cut which we can make with the lowest total capacity, and this lowest total capacity will be the bottleneck in this kind of we can say this whole max flow algorithm. So, minimum cut is the cut which we need to find, and we will be calculating the capacity that is going to be the lowest total capacity, and that is also known as the bottom up bottleneck capacity. So, here in this figure, as we have seen, if we talk about the cut A, as I have told you, it is having S and V1 in the set S and all other in the T. Now, if we talk about the capacities, the total capacities of the edges leaving set S in this cut from sink to source is 3 plus 4 plus 7, which is nothing but equals to 14, and here we have not added V2 to V1, because this edge goes in the opposite direction, which is from sink to source. We actually need it from source to sink, not in the opposite direction. So, if we talk about the cut A, so maximum possible possibility here is nothing but 14, which is 3 plus 4 plus 7. Moving further, if we look into cut B, the maximum possible flow is 3 plus 4 plus 3, which is 10 across this cut B, and this you can verify from your this figure. So, 3 plus 4 plus 3, which is equals to 10, that is the maximum capacity along with this cut B. And if we talk about the cut C, the maximum possible flow across this cut C is 2 plus 6, which is nothing but 8. So, if we checked all other cuts in the graph, we would not find any cut with the lower total capacity as compared to C, because the cut A is giving us 14, the cut B, as we have seen, is giving us 10. Now, the cut C, so these 3 cuts we have seen in our figure. So, the cut C is going to give us the maximum lowest total capacity. So, this cut C will be known as minimum cut, and now it is very obvious that which is the maximum flow which we can kind of push through this network. It will not go beyond 8, which is exactly what the max flow min cut theorem says. So, if we look into the kind of statement of max flow min cut theorem, the max flow min cut theorem says that finding the minimum cut in a graph is the same as finding the maximum flow, because the value of the minimum cut will be the same value as that of the maximum flow. So, we will be looking, we have with the help of this example, we have looked into different cuts, which is cut A, cut B and cut C. Cut A is giving us a flow of 14, cut B is giving us a flow of 10, while cut C is giving us a flow of 8. So, this is what kind of we can say min cut is, and so maximum flow which can be pushed through this particular graph, which we have taken as an example, is nothing but the equals to the capacity of min cut, which is 8 here. So, in this lecture we have tried to understood what actually max flow problem is. We have looked into kind of various terminologies and how we are going to represent this max flow graphs, what are the applications of these this max flow problem that we have also seen. And moving further, we also tried to understood the concept of max flow min cut theorem with the help of an example, and here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will be continuing with this maximum flow problem in my upcoming lecture. Till then, take care. Goodbye.